Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Agriculture, SOA, Master's Degree Programs, Master of Science in Food Safety and Quality Management, MSCFSQM, First Year, MVPI 001 Food Microbiology, Block-1 Fundamentals of Food Microbiology, Unit-2 Food Contamination and Spoilage, 2.0 Objectives. After reading this unit, we shall be able to times identify sources of food contamination, times specify food spoilage, its types, causative agents, and changes associated with it, times enumerate factors affecting the rate of spoilage, and times explain principles and methods of food preservation. 2.1 Introduction. Most foods are excellent media for rapid growth of microorganisms. There is abundant organic matter in foods, their water content usually sufficient, and the pH is either neutral or slightly acidic. Foods consumed by man and animals are ideal ecosystems in which bacteria and fungi can multiply. The mere presence of microorganisms in foods in small numbers, however, need not be harmful, but their unrestricted growth may render the food unfit for consumption and can result in spoilage or deterioration. There are many opportunities for food to become contaminated as it is produced and prepared. Many food-borne microbes are present in healthy animals, usually in their intestines, raised for food. Meat and poultry carcasses can become contaminated during slaughter by contact with small amounts of intestinal contents. Similarly, fresh fruits and vegetables can be contaminated if they are washed or irrigated with water that is contaminated with animal manure or human sewage. Some types of salmonella can infect a hen's ovary so that the internal contents of a normal-looking egg can be contaminated with salmonella even before the shell is formed. Oysters and other filter-feeding shellfish can concentrate Vibrio bacteria that are naturally present in seawater or other microbes that are present in human sewage dumped into the sea. Later in food processing, other food-borne microbes can be introduced from infected humans who handle the food or by cross-contamination from some other raw agricultural products. For example, Shigella bacteria, hepatitis A virus and Norwalk virus can be introduced by the unwashed hands of food handlers who are themselves infected. In the kitchen, microbes can be transferred from one food to another food by using the same knife, cutting board or other utensil to prepare both without washing the surface or utensil in between. A food that is fully cooked can become recontaminated if it touches other raw foods or drippings from raw foods that might contain pathogens. Microbes responsible for spoilage, the way in which food is handled after it is contaminated, can also make a difference in whether or not an outbreak occurs. Many bacteria need to multiply to a large number before enough are present in food to cause disease. Given warm, moist conditions and an ample supply of nutrients, a bacterium that reproduces by dividing itself every half hour can produce 17 million progeny in 12 hours. As a result, lightly contaminated food left out overnight can be highly infectious by the next day. If the food is refrigerated promptly, the bacteria multiply at a slower rate. In general, refrigeration or freezing prevents virtually all bacteria from growing and multiplying but generally preserves them in a state of suspended animation. This general rule has a few surprising exceptions. To food-borne bacteria, Listeria monocytogenes and Yersinia enterocolytica can actually grow at refrigerator temperatures. 2.2 Food contamination. Food contamination is the introduction or occurrence of a contaminant in food. A contaminant is any biological or chemical agent, foreign matter, or other substance unintentionally added to food that may compromise food safety or suitability. Among these contaminants are biological, chemical or physical agents in or condition of food with the potential to cause an adverse health effect. The contamination of food by chemicals is a worldwide public health concern and is a leading cause of trade problems internationally. Contamination may occur through environmental pollution, as in the case of toxic heavy metals, polychlorinated biphenyl, PCBs, and dioxins, or through the intentional use of chemicals such as pesticides, animal drugs, and other agrochemicals. Food additives and contaminants resulting from food manufacturing and processing can also adversely affect health. When foods are contaminated with unsafe levels of pathogens, chemical contaminants, or metals, they can pose substantial health risk to consumers and place severe economic burden on individual, communities, or nation. Cross-contamination of food is a common factor in the cause of foodborne diseases. Cross-contamination is the contamination of a food product from another contaminated source. Foods can become contaminated by microorganisms, bacteria, and viruses from many different sources during the food preparation and storage process. There are three main ways cross-contamination can occur: times food to food, times people to food, times equipment to food. 2.2.1 Contamination of living plants and animals. The internal tissues of healthy plants and animals are essentially sterile, including, in the case of animals, body fluids such as blood. Plants have a natural microflora associated with the surfaces of root, stem, leaves, flowers, and fruits. Invasion of healthy tissues and subsequent growth of microorganisms is prevented by times outer mechanical barriers, e.g. epidermis with an outer waxy layer, and outer corky layers, times internal chemical constituents that are antimicrobial, e.g. tannins, organic acids, and essential oils, times inert cell walls welded into tissues that are difficult to penetrate, times active cells with intact membranes. Plant materials are harvested in the living state and, as long as the mechanical barriers remain intact, can remain in storage at low temperature for several months without spoilage. Animals have a natural microflora associated with the skin, the gut content, and external openings, e.g. the mouth. Lymph nodes and liver may also be contaminated with invading microorganisms. Invasion of healthy tissues and subsequent growth of microorganisms is prevented by times epithelial barriers, e.g. stratified skin epithelium, epidermis, and intestinal mucosa, times the immune system consisting of the lymphatic system, white blood, corpuscles, and antibodies, times active cells with intact membranes, times presence of natural antimicrobials, e.g. lysozyme in tears, saliva, and egg white, times voiding mechanisms such as vomiting. Once an animal or plant is dead, the activity of the majority of factors, defense mechanisms that prevent microbial invasion of tissues by microorganisms ceases, and invasion is only temporarily hindered by mechanical barriers such as stratified epithelium or plant epidermis. Cell membranes are no longer active and leak cell contents, providing nutrients for microbial growth. To sources of food contamination, it helps to understand at which point our food might become contaminated, as this will provide us with a better impetus for taking personal responsibility to reduce the potential for further contamination. There are 5 main events that can cause food contamination. Food production. The use of chemicals, fertilizers, manures, etc. all have the potential to contaminate food as it is being grown. 2. Environmental factors. Bacteria, parasites, fungal spores, etc. travel in the wind, float in the water, hitch lifts with dust, and reside snugly in the soil. They are a part of nature's web of life and will always be a possible source of contamination if not dealt with appropriately as part of a consistent and dedicated approach to food hygiene. 3. Food processing. Whether in a large factory or in your own kitchen, food processing can be a major source of contamination. Areas used for processing need to be kept scrupulously clean, or cross-contamination can easily occur, especially with meat products. Natural bacteria residing in the intestines of animals are a major source of cross-contamination when mishandled. Fig. 2.1 Sources of contamination of food. 4. Food storage. Food that is stored incorrectly, for instance an uncooked chicken thigh resting next to a bunch of grapes, can be a source of transferring bacteria and other contaminants from one food to another. Food preparation. A great deal of food contamination occurs during the preparation stage. A sick person can pass on germs ranging from flu to gastroenteritis. A chopping board used for meat that is not washed and then used for vegetables is another source of possible contamination. Unwashed hands, dirty kitchen spaces, insects and rodents in the kitchen, etc. are all possible sources of food contamination. 2.3 Food spoilage. Spoilage of food may be due to chemical or biological causes. The latter include action of inherent enzymes, growth of microorganisms, invasion by insects, and contamination with trichinae and worms. About 1/4 of the world's food supply is lost through the action of microorganisms alone. The spoilage concept includes concepts about edibility, means the food is unfit to eat or fit to eat. Spoilage is decomposition. Many foods may not be decomposed, but harbor certain kinds of bacteria or their toxins in number or amounts which make the food poisonous and thus unfit for human consumption. The criteria for assurance in foods suitable for consumption are times the desired stage of development or maturity of the food times freedom from pollution at any stage in the production and subsequent handling of the food times freedom from objectionable chemical and physical changes resulting from action of food enzymes, activity of microbes, insects, rodents, invasion of parasites, and damage from pressure, freezing, heating, drying, and the like times freedom from microorganisms and parasites causing food-borne illnesses. Enzymatic and microbial activities are undesirable when they are unwanted or uncontrolled. An example is the souring of milk. If unwanted, it is spoilage. Yet, the same process is purposely used in the production of certain cheeses and other fermented products made from milk. 2.3.1 Types of spoilage. The food may become unacceptable due to the following factors. 1. Growth and activities of microorganisms, principally bacteria, yeasts, and molds. This is by far the most important and common cause of food spoilage. 2. Activities of food enzymes. Enzymatic browning is a common example. 3. Infestation by insects, parasites and rodents. 4. Chemical changes in a food, i.e. not catalyzed by enzymes of the tissues or of microorganisms. For example, the chemical oxidation of fats, producing rancidity, as well as non-enzymatic browning reactions in foods, like Maillard browning. 5. Physical changes or damages such as those caused by freezing, freezer, burn, by drying, caking, etc. 6. Presence of foreign bodies. 2.3.2 Classification of foods on the basis of stability. Foods are frequently classified on the basis of their stability as non-perishable, semi-perishable, and perishable. An example of the first group is sugar. Few foods are truly non-perishable. Hermetically sealed, heat-processed, and sterilized, canned foods are usually listed among the non-perishable items. For all intents and purposes, they belong there. However, canned food may become perishable under certain circumstances. when, by accident, there is a chance for recontamination following processing because of faulty seams of the cans, or through rusting or other such damage, so that the can is no longer hermetically sealed. Classified as semi-perishables are usually the dry goods, such as flour, dry legumes, baked goods, hard cheeses, dried fruits and vegetables, and even waxed vegetables. Frozen foods, though basically perishable, may be classified as semi-perishables provided they are freezer-stored properly. The majority of our food materials must be classified as perishables. This group includes meat, poultry, fish, milk, eggs, many fruits and vegetables, and all cooked or made food items, except the dry and very acid ones. 2.4 Role of microorganisms. Microbial spoilage of foods is the beginning of the complex natural process of decay that under natural circumstances leads to recycling of the elements present in the animal or plant tissues in the natural environment. 2.4.1 Microorganisms involved in spoilage. Microorganisms which may cause food to spoil include molds, yeasts, and bacteria. The contamination with molds, as a rule, is easily detected because of the presence of furry hyphae or thread-like structures which, in many instances, are colored. They often contribute a musty odor and flavor to the food they invade. Some molds, because of toxins they produce, are not altogether harmless. Semi-moist foods or foods with low water activity having been partially dehydrated and where the remaining water is sufficiently bound to hold the growth of bacteria are ideal for contamination by molds and yeasts. Yeasts are unicellular organisms of small sizes which multiply by budding. In general, sugars are the best food source for energy for yeast. Carbon dioxide and alcohol are the end products of the fermentation mediated by yeasts. Spoilage due to yeast may usually be recognized by the presence of bubbles and an alcoholic smell and taste. Bacteria spoil food in many ways, and it is not always possible to recognize the spoilage by sight, smell, or taste. Unfortunately, some of the bacteria that are important from a public health point of view may multiply to dangerously high numbers in food without changing the appearance, odor, or taste of the food. Disease-producing food has usually no decomposed appearance, but is certainly unfit for human consumption and must be considered to be spoiled. It is an important fact that almost any food will spoil if it is moist and not kept frozen. Spoilage must be expected within a wide temperature range. The various types of microorganisms as well as the genera, species, and strains vary in their temperature and food requirements. Thus, the bacterial flora of a spoiled food item will vary greatly. The origin of microorganisms also varies. The microorganisms may include the original flora of the particular food as well as contaminants added during handling, processing, transporting, storing, preparing, and serving. 2.4.2 Growth of microorganisms. The multiplication of spoilage organisms on or in the food materials depends on many factors: the type of organism involved, its ability to gain nourishment from the food, competition from other microorganisms, initial load, and environmental conditions. Microorganisms grow rapidly. We call it logarithmic growth. The time a bacterium takes to multiply, double its number, is known as its generation time, Fig. 2.1 A typical bacterial growth curve. 4 distinct phases occur in the growth curve: lag, log or growth phase, stationary phase, and death phase, Fig. 2.1 Bacteria need about 4 hours to adapt to a new environment before they begin rapid growth. In handling food, this means we have less than 4 hours to make a decision to either cool the food, heat it, or eat it. As microorganisms grow, they tend to form colonies. These colonies are made up of millions of individual cells. Once a colony forms, the food available to each cell is limited and excretions from these millions of cells become toxic to a microbe. This is the stationary phase. Some of the cells now begin to die. If we can control bacterial growth, we can control the major cause of food spoilage. The multiplication of spoilage organisms on or in the food materials depends on many factors: the type of organism involved, its ability to gain nourishment from the food, competition from other microorganisms, initial load, and environmental conditions. 2.5 factors affecting spoilage. Food is a chemically complex matrix, and predicting whether or how fast microorganisms will grow in any given food is difficult. Most foods contain sufficient nutrients to support microbial growth. Several factors encourage, prevent or limit the growth of microorganisms in foods. The most important are water activity, pH and temperature. Factors affecting microbial growth are divided into two groups: intrinsic and extrinsic parameters. Table 2.1. These factors affect the growth of microorganisms on foods. When spoilage of a food occurs under a given set of circumstances, not all of the different types of organisms contaminating a food are associated with the spoilage process. In fact, the spoilage flora always is dominated by just a few and sometimes only one organism. Components of the microflora compete with one another for the available nutrients, and the organisms with fastest growth under a particular set of circumstances will become dominant and give rise to the spoilage symptoms. Table 2.1. Intrinsic and extrinsic parameters affecting microbial growth. The component of the microflora which becomes dominant is determined by a complex interaction between the components of the contaminating microflora, implicit factors, the storage environment, extrinsic factors, and the physicochemical properties of the food, intrinsic factors. All of the factors that influence the growth of microorganisms have been dealt with as under. Time is included because under any given set of circumstances, spoilage takes a finite period to occur and equates with the storage life of a product. A knowledge of the intrinsic and extrinsic parameters should enable you to decide which broad group of organisms is likely to spoil a particular type of food, i.e., whether the food is likely to be spoiled by bacteria, yeasts, or molds. For example, foods that have a high water activity and a pH above 5.0 are likely to be spoiled by bacteria simply because under these conditions, bacteria grow the fastest. Foods with pH below 4.2 are likely to be spoiled by yeasts and molds even when the water activity is high. 2.5.1 Extrinsic factors. Extrinsic factors relate to the environmental factors that affect the growth rate of microorganisms. They are as follows. A. Temperature. Microbes have an optimum temperature as well as minimum and maximum temperatures for growth. Therefore, the environmental temperature determines not only the proliferation rate but also the genera of microorganisms that will thrive and the extent of microbial activity that occurs. For example, a change of only a few degrees in temperature may favor the growth of entirely different organisms and result in a different type of food spoilage and food poisoning. These characteristics have been responsible for the use of temperature as a method of controlling microbial activity. The optimal temperature for the proliferation of most microorganisms is from 150 to 400 C. However, many genera of microbes are capable of growth from 00 to 150 C, and other even microorganisms will grow at sub-zero temperatures. Still other genera will grow at temperatures up to and exceeding 1000 C. Microbes classified according to temperature of optimal growth include times thermophiles, high temperature-loving microorganisms with growth optima at temperatures above 450 C. Example, Bacillus stearothermophilus, Bacillus coagulans, and Lactobacillus thermophilus. Times. Mesophiles, medium temperature-loving microorganisms with growth optima between 200 and 450 C. Example, most Lactobacilli and Staphylococci. Times psychrotrophs, cold temperature-tolerant microorganisms which tolerate and thrive at temperatures below 200 C. Example, Pseudomonas and Acinetobacter. Bacteria, molds, and yeasts each have some genera with temperature optima in the range characteristic of thermophiles, mesophiles, and psychrotrophs. Molds and yeasts tend to be less thermophilic than bacteria. As temperature approaches 00 C, fewer microorganisms can thrive and their proliferation is slower. As temperature falls below approximately 50 C, proliferation of spoilage microorganisms is retarded as the growth of nearly all pathogens ceases. B. Oxygen availability. As with temperature, the availability of oxygen determines which microorganisms will be active. Some microorganisms have an absolute requirement for oxygen, whereas others grow in total absence of oxygen. Yet other microorganisms can grow either with or without available oxygen. Microorganisms that require free oxygen are called aerobic microorganisms, example, Pseudomonas spp, and those that thrive in the absence of oxygen are called anaerobic microorganisms, example, Clostridium spp. Microorganisms that can grow with or without the presence of free oxygen are called facultative microorganisms, example, Lactobacillus spp. C. Relative humidity. This extrinsic factor affects microbial growth and can be affected by temperature. All microorganisms have high requirements for water to support their growth and activity. A high relative humidity can cause moisture condensation on food, equipment, walls, and ceilings. Condensation causes moist surfaces, which are conducive to microbial growth and spoilage. Also, microbial growth is inhibited by a low relative humidity. Microorganisms, bacteria require the highest relative humidity of the various. Optimal relative humidity for bacteria is 92% or higher, whereas yeasts need 90% or higher, and for molds, the value of relative humidity is 85 to 90%. 2.5.2 Intrinsic factors that affect the rate of proliferation relate more to the characteristics of the substrates, foodstuff or debris that support or affect growth of microorganisms. These major intrinsic factors are A. Water activity. Water is required by microorganisms, and a reduction of water availability constitutes a method of food preservation through reduction of microbial proliferation. It is important to recognize that it is not the total amount of moisture present that determines the limit of microbial growth, but the amount of moisture which is readily available for metabolic activity of microbes. The unit of measurement for water requirement of microorganism is usually expressed as water activity, AW. Water activity is defined as the vapor pressure of the subject solution divided by the vapor pressure of the pure solvent, AU is equal to PP0, where P is the vapor pressure of the solution and PO is the vapor pressure of pure water. The approximate optimal AU for the growth of many microorganisms is 0.99, and most microbes require an AU higher than 0.91 for growth. The relationship between relative humidity, RH, and AU is RH is equal to AU times 100. Therefore, an AU of 0.95 is equivalent to an RH of 95%. Generally, bacteria have the highest water activity requirements of the microorganisms. Molds normally have the lowest AU requirements, with yeasts being intermediate. Most spoilage bacteria do not grow at an IGNOU below 0.91, but molds and yeasts can grow at an IGNOU of 0.80 or lower. Molds and yeasts are more likely to grow in partially dehydrated surfaces, including food. Whereas bacterial growth is retarded, approximate minimum IGNOU values for growth, organisms groups water activity, most spoilage bacteria 0.90, most spoilage yeasts 0.88, most spoilage molds 0.80, B pH. The pH for optimal growth of most microorganisms is near neutrality, 7.0. Yeasts can grow in an acid environment, but grow best in an intermediate acid, 4.0 to 4.5 range. Molds tolerate a wider range of pH, 2.0 to 8.0, although their growth is generally greater with an acid pH. Molds can thrive in a medium that is too acid for either bacteria or yeasts. Bacterial growth is usually favored by near-neutral pH values. However, acidophilic, acid-loving bacteria will grow on food or debris down to a pH value of approximately 5. 2 below, pH 5.2, microbial growth is dramatically reduced when compared from growth in the normal pH range, Fig. 2.2. Fig. 2.2 pH and growth of microorganisms. See oxidation reduction potential. The oxidation reduction redox potential is an indication of the oxidizing and reducing power of the substrate. To attain optimal growth, some microorganisms require reduced conditions while others need oxidized conditions. Thus, the importance of the oxidation reduction potential is apparent. Aerobic microorganisms grow more readily under a high oxidation reduction potential, oxidizing reactivity. A low potential, reducing reactivity, favors the growth of anaerobes. Facultative microorganisms are capable of growth under either condition. Microorganisms can alter the oxidation reduction potential of food to the extent that the activity of other microorganisms is restricted. For example, anaerobes can decrease the oxidation reduction potential to such a low level that the growth of aerobes can be inhibited. The nutrient requirements, in addition to water and oxygen, except for anaerobes, microorganisms have other nutrient requirements. Most microbes need external sources of nitrogen, energy, i.e., carbohydrates, proteins or lipids, minerals, and vitamins to support their growth. Nitrogen is normally obtained from amino acids and other non-protein nitrogen sources. However, some microorganisms utilize peptides and proteins. Molds are the most effective in the utilization of proteins, complex carbohydrates, and lipids because they contain enzymes capable of hydrolyzing these molecules into less complex components. Many bacteria have a similar capability, but most yeasts require the simple forms of these compounds. Minerals, micronutrients, are needed by all microorganisms, but requirements for vitamins vary. Molds and some bacteria can synthesize enough B vitamins to fulfill their needs, while other microorganisms require a ready-made supply. Inhibitory substances. Microbial proliferation can be affected by the presence or absence of inhibitory substances. Substances or agents that inhibit microbial activity are called bacteriostats, and those which destroy microorganisms are called bactericides. Some bacteriostatic substances are added during food processing, i.e., nitrites. Most bactericides are utilized as a method of decontaminating foodstuffs or as a sanitizer for cleaned equipment, utensils, and rooms. 2.5.3 Interaction between growth factors. The effects that factors such as temperature, oxygen, pH, and IGNOU have on microbial activity. may be dependent on each other. Microorganisms generally become more sensitive to oxygen availability, pH, and AU at temperatures near growth minima or maxima. For example, bacteria may require a higher pH, AU, and minimum temperature for growth under anaerobic conditions than when aerobic conditions prevail. Microorganisms that grow at lower temperatures are usually aerobic and generally have a high AU requirement, lowering AU by adding salt or excluding oxygen from foods such as meat, which have been held at a refrigerated temperature dramatically reduces the rate of microbial spoilage. Normally, some microbial growth occurs when any one of the factors that control the growth rate is at a limiting level. Yet, if more than one factor becomes limiting, microbial growth is drastically curtailed or completely stopped. 2.6 Deteriorative effects of microorganisms. Food is considered spoiled when it becomes unfit for human consumption. Spoilage is usually equated with the decomposition and putrefaction that result from activity of microorganisms. Some of the more common physical and chemical changes due to the microorganisms have been described under 2.6.1 Physical changes. The physical changes caused by microorganisms usually are more apparent than the chemical changes. Microbial spoilage usually results in an obvious change in physical characteristics such as color, body, thickening, odor, and flavor degradation. Food spoilage is normally classified as being either aerobic or anaerobic depending upon the spoilage conditions, including whether the principal microorganism causing the spoilage were bacteria, molds, or yeasts. Aerobic spoilage by bacteria and yeasts usually results in slime formation, undesirable odors and flavors, taints, color changes, and rancid, tallowy, or chalky flavors from the breakdown of lipids. Slime formation by certain species of bacteria or yeasts depends upon environmental conditions, especially those of temperature and AU. Color changes can be pigment oxidation resulting in a gray, brown, or green color. Physical deterioration through aerobic spoilage by molds results in sticky surface of many foods. A filamentous appearance, frequently referred to as whiskers, can also occur as a result of physical deterioration. Discoloration from molds can give surface colorations, such as creamy, black, or green. Deterioration from molds can affect appearance of lipids of foods in a way similar to that of bacteria and yeasts and will produce musty odors and alcohol flavors. Aerobic spoilage of foods from molds is normally limited to the food surface where oxygen is available. Therefore, mold surfaces of foods such as meats and cheeses can be trimmed off and the remainder is generally acceptable for consumption. This is especially true for aged meats and cheeses. When these surface molds are trimmed, surfaces underneath usually have limited microbial growth. However, if extensive bacterial growth occurs on the surface, penetration inside the food surface usually follows and toxins may be present. Anaerobic spoilage occurs within the interior of food products or in sealed containers where oxygen is either absent or present in limited quantities. Spoilage is caused by facultative and anaerobic bacteria and is expressed through soaring, putrefaction, or taint. Soaring occurs from the accumulation of organic acids during the bacterial enzymatic degradation of complex molecules, carbohydrate. Also, proteolysis without putrefaction may contribute to soaring. Soaring can be accompanied by the production of various gases. Examples of soaring are milk, round sour or ham sour, and bone sour in meat. These meat sores or taints are caused by anaerobic bacteria that may originally have been present in lymph nodes or bone joints, or which might have gained entrance along the bones during storage and processing. 2.6.2 Chemical changes. through the activity of endogenous hydrolytic enzymes that are present in foodstuffs and the action of enzymes that microorganisms produce, proteins, lipids, carbohydrates, and other complex molecules are degraded to smaller and simpler compounds. Initially, the endogenous enzymes are responsible for the degradation of complex molecules. As microbial load and activity increase, degradation subsequently occurs. These enzymes hydrolyze the complex molecules into simpler compounds that are subsequently utilized as nutrient sources for supporting microbial growth and activity. Oxygen availability determines the end products of microbial action. Availability of oxygen permits hydrolysis of proteins into end products such as simple peptides and amino acids. Under anaerobic conditions, proteins may be degraded to a variety of sulfur-containing compounds, which are odorous and generally obnoxious. The end products of non-protein nitrogenous compounds usually include ammonia. Other chemical changes include action of lipases secreted by microorganisms, which hydrolyze triglycerides and phospholipids into glycerol and fatty acids. Phospholipids are also hydrolyzed into nitrogenous bases, and phosphorus lipid oxidation is also accelerated by extensive lipolysis. Most microorganisms prefer carbohydrates to other compounds as a source of energy. When available, carbohydrates are more readily utilized for energy. Utilization of carbohydrates by microorganisms results in a variety of end products such as alcohols and organic acids. In many foods such as sausage products and cultured dairy products, microbial fermentation of sugar that has been added yields organic acid, example, lactic acid, which contribute to their distinct and unique flavors. 2.7 Different types of food spoilage. Food undergoes different types of spoilage depending on its composition as shown in Table 2.2. Table 2.2 Types of food spoilage. Look at the screen. 2.8 Common methods of food preservation. Principles of food preservation include the following. I. Prevention or delay of microbial decomposition by keeping microbes out. Asepsis. By removal of microbes, e.g. filtration. By reducing the rate of microbial growth, e.g. by low temperature, drying, anaerobic conditions and chemical inhibitors. By killing microbes, e.g. by heat or radiation. 2. Prevention or delay of self-decomposition of food by inactivation of food enzymes, e.g. blanching. By prevention of chemical reactions, e.g. by using antioxidants. Table 2.3 Methods of food preservation, operation and intended effect. Cleaning, washing reduces microbial load. Cold storage, below 8 degrees, prevents the growth of most pathogenic bacteria, slows the growth of spoilage microbes. Freezing, below 10 degrees, prevents growth of all microbes. Pasteurizing, 60 to 80 degrees, kills most non-sporing bacteria, yeast and molds. Blanching, 95 to 110 degrees, kills surface vegetative bacteria, yeast and molds. Canning, above 100 degrees, commercially sterilized food, kills all pathogenic bacteria. Drying, stops growth of all microbes when AW
below 0.60. Salting stops growth of most microbes. Syruping, sugars, halts growth when AW greater than 0.70. Acidifying halts growth of most bacteria. Effects depend on acid type. AU denotes water activity. Food preservation aims at preventing the microbial spoilage of food products and the growth of the food-borne pathogens. Thus, the two principal goals of food preservation methods are I. Increasing the shelf life of the food and 2. Ensuring the safety for human consumption. There are a variety of food preservation methods. Table 2.4 consolidates the methods and details are given here. 2.8.1 Heat. Heat kills microorganisms by inactivating their proteins and by changing the physical and chemical properties of their proteins. The most common use of heat is in the process of canning. The food product is washed, sorted, and graded and then subjected to steam heat for 3 to 5 minutes. This last process, called blanching, destroys many enzymes in the food product and prevents further cellular metabolism. The food is then peeled and cored, and diseased portions are removed. For canning, containers are evacuated and placed in a pressurized steam sterilizer, similar to an autoclave at 121 degrees Celsius. This removes especially Bacillus and Clostridium spores. If canning is defective, foods may become contaminated by anaerobic bacteria, which produce gas. These are species of Clostridium and coliform bacteria, a group of gram-negative non-spore-forming rods which ferment lactose to acid and gas at 32 degrees Celsius in 48 hours. 2.8 to low temperature. Exposure of microorganisms to low temperatures reduces their rates of growth and reproduction. This principle is used in refrigeration and freezing. Microbes are, however, not killed. In refrigerators at 5 degrees Celsius, food remains unspoiled. In a freezer at -5 degrees Celsius, the crystals form tear, shred, and thereby may kill microorganisms. However, some are able to survive. Salmonella spp and streptococci survive freezing. For these types, rapid thawing and cooking is necessary. Deep freezing at -60 degrees Celsius forms smaller crystals. It reduces biochemical activities of microbes. Blanching of fruits and vegetables by scalding with hot water or steam prior to deep freezing inactivate plant enzymes that may produce toughness, change in color, etc. A brief scalding prior to freezing also reduces the number of microorganisms on the food surface by up to 99%, enhances the color of green vegetables. 2.8.3 Drying or desiccation. Water from foods is removed in different ways. It may be done by spray dryer, which expels a fine mist of liquids such as coffee into a barrel cylinder containing hot air. A heated drum may be used onto which liquids like soup may be poured. Another example is a belt heater that exposes liquids like milk to a stream of hot air that evaporates water and produces dried milk solids. A common process of freeze-drying or lyophilization is used these days. The food is deep frozen, after which the water is drawn off by a vacuum pump in a machine. The dry product is then sealed in foil and is reconstituted with water. This method is very useful for storing, transporting, and preserving bacterial cultures. 2.8.4 Osmotic pressure. The principle of osmosis is applied in the age-old traditional method of adding salt or sugar to pickles, preserves, and jams. Foods are preserved by adding salts and sugars to them. These solutes remove the water out of microbial cells, causing them to shrink, thus stopping their metabolism. Jams, jellies, fruit syrups, honey, etc. are preserved by using high sugar concentration. Fish, meat, beef, and vegetable products are preserved with salt-mediated process. 2.8.5 Chemical preservatives. The most commonly used preservatives are the acids, such as sorbic acid, benzoic acid, and propionic acid. These check mainly the growth of yeasts and molds. Sorbic acid is used for preservation of syrups, salads, jellies, and some cakes. Benzoic acid is used for beverages, margarine, apple cider, etc. Propionic acid is an ingredient of bread and bakery products. Sulfur dioxide, as gas or liquid, is also used for dried fruits, molasses, and juice concentrates. Ethylene oxide is used for spices, nuts, and dried fruits. 2.8.6 Radiation. Ultraviolet UV radiation is used in meat storage facilities, which reduce surface contamination on meat products. Gamma rays are also used for some meat products. 2.8.7 Anaerobiosis. Packaging of food products under anaerobic conditions. Anaerobiosis is effective in preventing aerobic spoilage process. Vacuum packing in an airtight container is used to eliminate air. 2.8.8 Controlled atmosphere. Atmospheres containing 10% CO2 are used to preserve stored food products, such as apples and pears. This checks fungal growth. Ozone can also be added. 2.8.9 Other methods. These are asepsis, i.e. washing utensils that come in contact with food, and filtration and centrifugation to remove microbes. Filtration is used for fruit, juices and other drinks. Bacteriological filters are used in industries. 2.9 Let us sum up. Food spoilage is caused by microbial growth in foodstuffs, chemical reactions within the food itself or between the food and its environment, or the presence of foreign material in the food. Food spoilage is a complex process, and excessive amounts of foods are lost due to microbial spoilage even with modern-day preservation techniques. Despite the heterogeneity in raw materials and processing conditions, the microflora that develops during storage and spoilage of foods can be predicted based on knowledge of the origin of the food, the substrate base, and a few central preservation parameters such as temperature, atmosphere, AU, and pH. Based on such knowledge, more detailed, sensory, chemical, and microbiological analysis can be carried out on the individual products to determine the actual specific spoilage organism. Generally, foods carry a variety of organisms of which most are saprophytic. Their presence cannot be avoided since these are mostly from the environment in which the food is prepared or processed. Also, their complete elimination is difficult. However, it is possible to reduce their number or decrease their activities by altering the environmental conditions. A knowledge of the factors that either favor or inhibit their growth is therefore essential in understanding the principles of food spoilage and preservation. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.